Good morning. My name is Shreyas Sanath Kumar Atcham. I am presenting my literature survey on phase change memory architectures. Memory is any electronic or mechanical circuitry used to store data, mostly binary. Memory is the most important and essential subsystem of any computational system, without which it is handicapped. It is used everywhere from on-chip cache to disk storage to flash storage to high-speed solid-state drives in large server farms. Memory can be broadly classified as volatile memory, where the data is lost when the power supply is disconnected to the device; non-volatile memory, where the data is retained when the power is lost; read-only memory, where the data can only be read and cannot be written to the device, or very difficult to write to the device; or random access memory, where data can be written and read at equal time intervals. The main memory of a system is comprised of random access memory. Different memory systems in an embedded system have different characteristics and hence use different types of memories. There are many different memory technologies used in the present arena of embedded systems as follows. Mask programmed ROM, where the data is written during fabrication of the memory and cannot be erased or overwritten. EEPROM and EEPROM. It is a read-only memory where it can be erased with UV light or electronically respectively. DRAM. Here the data is stored in small capacitors. The data is written by either charging or discharging the capacitors. Memory cells are very small and compact and have a good memory density. Due to leakage current, the data must be refreshed frequently to retain the data. SRAM. Here the data is stored in a cross-coupled inverter. They are very efficient and have low standby power. Flash. Here the data is stored by energizing the floating gate of a MOS transistor. It is broadly used as a cache for mass storage technologies like disk drives, or recently as a replacement for the mass storage device. Phase change memory is a new memory technology on the rise in the world of embedded systems. It is a form of non-volatile memory. They are made up of phase change materials like chalcogenides to store data. The memory cell in PCM is as shown in the figure A. It has a chalcogenide material and a resistive heating element between two metal plates. When a current is passed through this memory cell, the junction between the chalcogenide material and the resistive heating element is heated up. By controlling the magnitude of the set current, the duration and its ramp down, the chalcogenide material can be cooled quickly to transform to amorphous material, which is termed as reset, or cooled slowly to transform and grow crystalline structures, which is called the set state. This is controlled by a transistor in series with the memory cell, as shown in figure B. DRAM has been the technology used in main memory for many generations. With the advance in process technology, the need for large capacity of main memory has increased. As DRAM has issues when shrunk below 40 nanometer, the memory density of DRAM cannot be increased further. Additionally, the need for periodic refresh to retain data causes high energy consumption. To overcome this, different memory architectures must be implemented with a new memory technology. Presently, phase change memory has been the top contender for this. Researchers have devised different memory architectures with phase change memory for different use cases, like for enhancement of present PCM technology, or to prime PCM to be a replacement for present memory technologies, or to build phase change memory into present memory systems to improve its performance. Security refresh. The biggest issue with PCM is its limited write endurance. When a malicious code makes multiple write requests to the main memory, a few memory locations gets returned to repeatedly, hence decreasing the device lifetime. To overcome this, the physical address and the memory address are decoupled and a new layer called randomizer is added in the middle as shown in the figure. Randomizer does the work of periodically randomizing the physical address to memory address table, hence keeping wear level in the device uniform. This brings the device life cycle from 42% of max lifetime to 82% of max lifetime of phase change memory. Multi-level cell, or MLC in short, is a technique which is used to store multiple bits in a single memory cell. This can be implemented in PCM, which would improve the storage capacity by 100% and introduce an additional read latency. To have the advantages of having PCM without the delay cost, a hybrid MLC/SLC, that is single level cell, technique is implemented where the data stored in the memory cell can be dynamically changed from MLC and SLC. When large volumes of data that have no need for fast access time is to be stored, then it is implemented in MLC technique. When there is a need for speed in read of data and critical data, then it is stored using SLC technique. When this technique is made aware to the OS and implemented as per requirement of the memory system, then the gain in memory density is more than the read latency of critical data. For PCM implementation in main memory to have positive performance enhancements without the drawbacks of phase change memory, heterogeneous memory systems are designed. Here, both DRAM and PRAM is used with the help of a hybrid memory controller. Depending on the architectural requirements and required characteristics of main memory, the memory controller dynamically stores the data in either DRAM or PRAM depending on potential of writes and frequency of reads, criticality of data and energy profile of the system. This implementation can have the energy density of PCM with the write endurance of DRAM. PDRAM is a heterogeneous main memory system with PRAM and DRAM. It uses a hybrid memory controller which has a page allocator and a page swapper. To maintain wear leveling, the page allocator has three lists, that is, free, used free, and threshold free. When a new request for a page is received by the memory allocator, a page in the free list is allocated, and when a page is released, it is sent to the used free list. When a page is returned to a threshold number of times, it is then sent to the threshold free list. When the free list is out of memory locations, it is merged with the used free list. When the combined list is out of memory locations, it is merged with the threshold free list, and then they are all moved to the free list. When a process page swap, when this is received, the probability of multiple writes is very high. Hence, the memory controller decides to move the page to the DRAM as it has no write endurance issues. When the number of writes are low, another swap interrupt is issued which moves it back to PCM. This policy is known as hybrid memory policy. This together with hybrid memory controller has the advantage of having high memory density of PCM but does not have write endurance problems of PCM. "3D ICs is a new area of research where the memory module is built over the processor chip in multiple layers. Here, the memory must work in high temperature environment, which causes DRAM to have large leakage currents and have large power consumption. Consequently, due to high temperatures, the power consumption for writing data to PCM is decreased drastically, hence making heterogeneous memory systems perfect for 3D ICs. Here, as discussed before, wear leveling techniques are implemented to increase device lifetime and frequent write requests are returned to DRAM to improve PCM lifetime. When data is to be stored with less number of writes, it is then stored in PCM. This technique thus provides the advantage of high memory density in 3D ICs. Present memory technology implementations are shown in figure A and figure B. When PCM is to be implemented for high performance main memory directly, as shown in figure C, it causes issues like low device lifetime and high read and write latency. So to overcome these shortcomings, DRAM and PCM hybrid is implemented. To improve write endurance of PRAM, lazy write organization is implemented, where when multiple write requests are issued to the same memory location, it is stored in DRAM and a location in PCM is assigned for it. When requested for the data, it is forwarded to the DRAM. After a specific amount of time, the data in PCM is updated with the one in DRAM. To decrease the number of writes, line level read is implemented, where when a request is issued to update data, instead of writing a whole page, only the necessary lines are written, hence avoiding excess writes to memory. Fine-grained wear leveling is implemented, where the writing memory block size is decreased, and previously discussed wear leveling algorithms are used to control wear leveling more accurately. With all the architectures and implementations discussed here, the PCM technology is primed to replace existing memory technologies in the near future. It is set to drive the next revolution in embedded systems development. Thank you.